Welcome back, Herbalots. So today we're going to finish the mission that we tried to do last time and we were somewhat unsuccessful. Namely, we're going to try to launch a satellite and to actually have it talk into deep space. This is our satellite that has... let's see if I can... It has our infrared telescope, and I've added a few other instruments on board as well. Seem to have found an interesting camera mode, but I can't seem to access them. That's okay. It'll be fine. We'll just wait until the clamshell's deployed before we use any of them. So we'll start our gravity turn. You'll notice this is a little bit more advanced than some of the previous satellite bases that we've used. Got a little shimmy. Gonna lock it. I'm gonna go straight up. We are not stable enough. We're shaking too much, and so we'll lose some efficiency, but we have a lot of delta V to spare. What we do not have to spare is ability to rotate upside down, which I'm afraid is what we would do if we tried to point this a little bit better. Real rockets are very complex to get them built right. It's not for nothing that it's taken years. Falcon Heavy took years to build. Years. And it's not for nothing that it took that amount of time. So the solid rockets will burn out, and then shortly thereafter, actually, I'm high enough I can afford to tilt some. We almost did a Falcon 1 Flight 3 there. Falcon 1 Flight 3, the second stage fired right as the first stage was still pushing just a little bit. They separated, and the second stage wasn't going quite fast enough, and it actually, the first stage intersected the second stage again, and it caused it to be off just a wee little bit. Let's go ahead and deploy the clamshell. See our satellite. Big difference. You notice that big honking antenna that we've got now. Also have a number of other instruments. I don't know why I put an accelerometer on there, but we have an accelerometer. The big one is this one, the gravity sensor. I'm not quite sure why we lost electrical charge. Well, it's a good thing we have solar panels going. Yeah. Oh, it's because we were transmitting. Bad me. I shouldn't be transmitting while I'm... Oh well. It'll be fine. We're gonna be just fine. It's really not a very great trajectory we're on. Can't run an atmosphere scanner while you're in space. How about that? Okay. Actually, let's turn on the allow partial. Hello there, Moon. Isn't this pretty? Firing into the sun. That's eventually what we're going to do is kind of orbit the sun, so... Well, we are going to orbit the sun. There's no kind of about it. Oh, that was not a very great trajectory, but that's okay. Okay. How badly did we do? Answer is pretty bad. Okay, so we need to burn such that our final trajectory heads out behind us. Actually, we need to burn right about where we're at right now. No. That is too much. We can optimize this a little bit less. Let's see here. Are we... So this still... Okay. That's about the right burn. We need it to go a little bit earlier. It's pretty close. Still too much of a burn. So we're aiming for a point that you can't actually see right now, but it's right between Kerbin and Eve's orbit. Last time I almost nailed this perfectly. Too bad the satellite didn't work. Silly thing, it wanted to actually have a big enough antenna to talk to the ground. I don't know what it was thinking. Okay, right there. Perfect. Okay, I'm gonna go with it. Ship it. "45-second burn. How much fuel do we have?" I don't know. It's gonna be pretty close. Nah, actually we have plenty of Delta V. Plenty. Actually, let me try to get another gravity scan. Ooh. That was a new one. And I almost missed my burn. Bad me. This is why they don't do it in real life, because you would get confused. You gotta be hyper focused if you're gonna do a time sensitive burn like this and not be messing around. But I do it for you guys. Alright, so what the sensor here that we have is a gravity detector. They actually do fly these, a couple of them, although they usually don't take this form. They usually take the form of two different types of satellites that are watching each other. Oops. What did I just... This is bad. Well, let's slow down a little bit. Okay, how are we looking on the big picture? It's a good trajectory, and I'll take it. Are we going by any planets or anything? Nope. Looks good. Perfect. Now is a good time to transfer some of this data. So the gravity scans, they can tell you a lot about what is underneath the surface. You can use these to detect stuff like oil deposits, or mountains, or just unusually dense material. The gravity, we'd like to think that it's uniform across the planet, and it's pretty close, but has some variations on the order of a few fractions of a percent. The moon has a lot of variation. It actually goes up to about 1% variation, and because of that, satellites that are orbiting the moon are extremely unstable. Unless you happen to be in the perfect orbit, it might only last for a matter of days. So a lot of the Apollo spacecraft, they took gravity scans while they were, or they dropped off satellites on their way back, and some of the probes only lasted for like a couple of weeks because they were placed in particularly poor paths. They've since discovered that certain angles are more conducive to long-term moon orbiting satellites than others, and so they will aim to do those for those times that they're trying to head into space. If they want it to last for a long time, the modern moon orbiters all use those special orbits. I think there are like 3 or 4 inclinations that work particularly well. But the non-uniformity can cause some really interesting effects. It causes the orbital planes to precess, for instance. Okay, so if this was a real mission, this would be the time where this lower booster would drop itself off and re-enter, and the upper stage would continue on for the primary mission. The aeroshell will actually be kept off, but in Kerbal Space Program, unlike real life, these highly efficient rocket boosters can hold their fuel for forever. In real life, they use cryogenics, so they have a limited lifetime. Let's see if I can collect one more useful. Still over the water. Okay, managed to log all that data. We're still above the water. I don't think that's going to change too much. Okay, well, we'll forget it. We've already collected a decent amount of science from this. Try a long future. Oh, good. Got some more data. That's awesome. Real space missions don't... Actually, transmitting the data back is a concern, but it takes a lot longer to do than in Kerbal Space Program. So they will be sending data continually, but that doesn't make for a very good game. You know, it's like ion engines in this game are somewhat unrealistic. They accelerate a lot faster than real-life ion engines. But if you're accelerating because of the way the game works, you have to be playing in relatively slow time, and you can't be having the engine fire for years. Nobody would want to do that. Well, we'll talk about ion engines a little bit more. We'll do some spacecraft with ion engines. Okay, well, we're getting plenty of science, and we're going to start to get into some of the really fun stuff that you can do. But for now, let's just head out of the system. Well on our way. You notice how fast we're leaving when we leave the system. Okay. So we are now in deep space. Yay! Let's do one round of science. Why can't this run? I have the power. I guess you can't do a gravity scan of... No. Huh. Oh, I'm in time warp, that's why. Silly me. There's the atmosphere scan, which of course we've already done. Get accurate gravity scans of the sun. And we're going to go ahead and start tracking objects. Okay. Let's just go ahead. I think we're heading this direction. Nope. We're going to accelerate just a smidgen. Because we're too low. Hopefully we have enough fuel to do all of this. Okay. Well, we're now touching here, so we'll give this a shot. See, we're detecting all of these asteroids all over the place. And we still have a clear connection to Kerbin. Yay! This is actually a relay satellite, so it could, in theory, be used to communicate with some far-out satellites. Not really much of a reason why I chose to do that. Okay, we want to slow down. Actually, let's keep going until we're at the low point overall. We're still in good communication. Yay! Come on. Up, and we have achieved the desired orbit. So we're going to complete that contract with just a little bit of fuel to spare. Oh, thank goodness. So in real life, infrared satellites like this, they tend to be placed at what's called the Lagrange 2 point. So for a real space body, what they call a 3-body problem, there are 5 special points that are stable that aren't directly connected to the host planet, but you can stay at or near these points relatively easily. The first one, Lagrange 1, is the point. So here's Kerbin. It's a point where the gravity is equal between the Sun and Kerbin, or Earth, or any two sufficiently heavy bodies. So it'll be maybe about here. And so in real life, you could stay at that point for kind of forever. You have to use a little bit of fuel to keep yourself right on the perfectly balanced point. So that's a Lagrange 1. Lagrange 2 is back behind the planet. Lagrange 3 is on the opposite side, so Lagrange 3 would be right about here. And then 4 and 5 are along the orbital tracks at 60 degrees. And these ones are the most stable of all of them. But Lagrange 2 tends to be a good spot for infrared satellites because it can stay close to Earth, real Earth, close enough to communicate a lot of data, but it can be far enough away to be a little bit cooler. And so the James Webb Space Telescope is actually in Lagrange 2 point because it's an infrared satellite. It's going to be there. It's not there yet because it hasn't launched. And it will allow it to work well. Work better that way. So, yeah. See if there's any temperature. Nope. We got everything. Anyways, that's about all we got for this time. We finally succeeded in making this mission work. One thing I didn't add is we have relay satellites like this in Mars. All of the orbiting satellites around Mars can relay data, and so the landing satellites, where weight and the structure is a lot harder than it is for an orbiting satellite, they don't have to take as big of an antenna. They just talk to the relay satellite, and the relay satellite forwards that data back to Earth, and it's able to have a much, much higher communication rate because of that. So all kinds of good stuff can happen. Let me just check the... So it looks like in order to get the credit, we have to... Oh! Just let time play, and we'll map out these satellites. So this satellite here is very reminiscent of the WISE satellite, W-I-S-E, which was an infrared survey satellite that was used to primarily to track celestial objects, but they also were able to find a whole bunch of new asteroids with it. Oh, we got all the data that we needed. And so the WISE satellite orbited much closer to Earth for some period of time. They were able to detect all kinds of cool stuff out in deep space, as well as a number of asteroids. So it's, I suppose that's what this is trying to do. Real life telescope like this, though, would be probably more to observe stars and dust clouds than asteroids. A little part clipping here. It's one of the things that makes Kerbal Space Program a lot easier than real rocket science. Okay, so we got our mission completed, and I think this is about all for now. Thank you very much for joining me, and let me know whatever questions you guys have in the comments, and I will see you next time. Take care.